It will come in a few seconds. All right, so welcome to another IAA seminar, Institute of Astrophysics in Andalusia colloquium series. Today it's my pleasure to have Dr. Jian Lo, named Paul as well. Paul did his PhD in Chalmers University in Sweden, in Gothenburg, under the supervision of Professor Jonathan Tam. And then he finished in January 2024, so just this year. After that, he moved to Arcetri Observatory at INAF, is the institution, to work with mighty electron. Paul's main interests are in massive star formation, so he does that mainly through observational point of view, using radio interferometers, ALMA observations, and such. But also, he's very much interested in the magnetic fields of these systems. So today, he's going to tell us more about these elusive observations and the path to massive star formation. So please, Paul, take it away.
Thank you very much for Ruben's introductions, and I'm really happy to be here. And thank you for giving me a chance to present and share about my project here, especially working in Arcetri. So I will be mainly focusing on one of the massive star forming regions, G31, and I'm really grateful, and of course with all the guardians and also the help from all the collaborators here, which are listed from especially Michael Bertrand, Joseph Miguel Gerard, Daniel Gali, Ricardo Cesaroni, Luca Masachelli, and etc. like Ray Furia, Alberto Sana, and Gabriel as well. So for this talk, I would want to give an outline, which is to really give an introduction to setting the stage, what interesting about massive star formation and why we want to study magnetic field and their impact on high mass star formation. And then I'm going here to focusing on one of the regions, as I mentioned in the beginning, which is G31.41, massive star forming regions. In particularly in this work, I'm going to focus in two aspects, which is the first one is the magnetic field orientations toward the G31 hot molecular core. And secondly, we're also looking into magnetic field properties in the filaments in the larger scale environment of G31. And in this case, from here, we want to learn what is the implications of the high mass star formation from a multi-scale view perspective on G31. And I will give a summary of this work. And towards the end, I also want to highlight a few other works, which I've been also working on to really studying the impact of magnetic field in high mass star formations. So to begin with, actually, I want to first bring you to the question, why study massive star formations? I mean, one of the things is these massive stars are actually having at least 8 times the solar mass of our sun, which is, of course, this is also an empirical cut, which is about 8 solar mass. They are rare, but they play a very important role in different aspects. For example, in this exotic life cycle of the massive stars, one of the things you have the supernova, will explode, and it's actually refreshing the universe with all the chemical species. And also we know that the massive stars are really important in this synthesis of heavy elements as well. So this is actually very important, and also the star forming regions during the young stage of these massive stars, this really energetic outflow and stellar winds also will be affecting the nearby next generation star formation as well. However, many open questions remains, and in particularly what we are going to study is the magnetic field. But before we going into these, we actually want to go back a little bit and understand some of the main steps in the high mass star formation. And in fact, if we want to understand high mass star formation, we have to go back to one of the, I would say, more standard picture, the low mass star formations, because especially one of the major classes of high mass star formation actually also based on the low mass star forming picture as well. So here we know that stars normally form in molecular cloud. Here's just one of the example, which is the Pied Nebula. And from here, we see that when there's the region which is really gravity dominating, we will form into prestellar cores. And from there, we will lead to the formation of protostellar cores when the first protostar objects formed. And especially when, because of the conservation of the angular momentum, we will lead to the formation of the disk. At the same time, outflows start to emerge. And this is one of the important process, which is also channeling some radiations pressure from the stars as well, especially when we go to the high mass regime. And as this output continues to emerge and dispersing the neighboring materials, it will open up the angles. In the end, when dispersed, all the materials will live with a territory star system, retaining the circumstellar disk as well. So this is some of the major, many of the main pictures. However, this actually leads to some of the open questions in massive star formations. So for example, one of the questions that we links to is what's the relationship between massive star formation to star cluster formation? In general, we see massive star regions forming clustered, but can we actually form in isolations? And in fact, I mean, one of the sources which I have been leading with ALMA study in G20.2 might be one of the first example, which could be forming in isolations. Another question is, does massive star formation follows a scale-up version of the low mass star forming picture, as I just showed in the last slide, which we think that could be the core accretion model, which support a very dense and massive core. On the other hand, you may have more competitive accretion model, which is really drawing material from the much larger scale environments. And for also one more question is, for example, is to what extent the small scale physical chemical conditions really care about the larger scale environments? Because we know that the star formation is a multi-scale processes. And also we also want to understand whether the larger scale conditions may be influencing or actually constraining the smaller scale as massive star formation properties. However, to me, at least what I'm interested in, I think one of the questions, as I think I will lay this out from one of the EPOS conference, which Maite, I think, in her abstract laid out this question. Does the magnetic field play a relevant role in regulating high mass star formation at all scales, from large or cloud scale to small circumstellar scales? I think this question, I would say, by really understanding this question, we're able to really proceed or make progress to understanding those questions I just laid out above. So one of the first questions I actually want to tackle in this project, or I want to present in this seminar, is what is the magnetic orientation from cloud to these scales? So this is a picture that we can kind of reference from, is from Makita et al. 2007. What we can see from the cloud scale, the magnetic field should be quite uniform and ordered. As this going to the core scale, where gravity really contracting, what we are seeing is conical hourglass morphologies. And we have the disk and really going from the toroidal to a toroidal field morphology, which is really twisting the field lines here. So you can also see from the scale here, which is going from the cloud, we will see the parsec scale to thousands and even to 100 scale. So we can see how the magnetic field orientation changes. And one thing also we want to think is that in observationally, we can see that if this is ordered, we should see a somewhat self-similar magnetic field orientation from the large to the smaller scales. And in fact, there is some study which might indicate this. Of course, one of the examples is studied by Li et al. In 2015, which is see this self-similar magnetic field orientation from large to small scale to NGC 634 using different instrumentations. And of course, the source that I will be discussing more in depth, which is the G31.41, as what first seen in Joseph Miguel Garage 2009, which is really nice, one of the example of hourglass magnetic field morphology in high mass star forming regions. And later we can also see in Maite Bertrand in 2024, we also see this self-similar magnetic field from the core all the way to circumstellar scales, which is clearly seeing also this nicely hourglass morphology. And this also can be especially fit with this model by Daniele Galli and Shu 1993. So this actually suggests that the magnetic field seems to indeed playing an important role from across different scales as well. So now we will go in depth to this source, which is G31.01. So at the smaller scales, actually starting from the smaller scales, this is actually at the source distance of 3.75 kiloparsec, which is very luminous, which is studied by Myra. And in 2009, we found it to be like at least 5 times 10 to the 4 solar luminosity. And you can see from this figure, we also have the hot molecular core, and this is one of the very chemically rich hot molecular core found in high mass star forming regions, which have been numerously studied by different people here. And also we can also see there's an ultra compact H2 region, which is quite close to the hot molecular core regions as well. And this molecular core shows really info signature, and actually when we're looking into rotational velocity, I'm actually seeing that this actually have a rotational spin up. And also at the smaller scale of this paper, we also found that there's like a velocity gradient across the core, which is shown in Bertrand et al. 2019. And of course, as I mentioned, there's different outflow and inflow signature. And even at the smaller scale, we see fragmentations, which is this, especially this core is fragmented into 4 protostellar objects, which is denoted as A, B, C, and D. And also in the same study, there are also other continuum sources identified. For example, one of the strongest one is the northeast source over there as well. So this is one of the summary on the smaller scales. But then now when we look to the larger scales, which is here, which is a figure taken from Bertrand et al. 2022, we can see this really nice hot filament system, which is at the P1 location around that. This is where the G31 hot molecular core is. And also the white contour here, which is the N2H plus and overlaying on top of the color scale of the 8 microns, which you can see this half filament is appears as 8 micron dark absorption feature, and the N2H plus really quite coincide on these features. And especially we also identified here from Bertrand et al. 2022, we identified 4 filament arms, which is denoted as F1, 2, 3, and 4. And also from the integrated intensity map of the N2H plus, we see 2 really strong peaks, which is P1 and P2. And of course, the P2 seems to be does not really associate with any protostellar objects. And also, if you look closely here, the 8 micron features of the main filaments that host the G31 hot molecular core, we see this kind of arc-shaped morphology, which seems to be quite closely traced the radiation from the bubble towards the west of it. So it seems to be might be some interactions from the bubble on the filaments, which is, of course, this bubble is identified as an infrared bright feature here in this figure. So one of the things we want to study this, we actually observe this region with JCMT PO2, which is at 850 microns, which we also get the polarized dust emissions. So on the left here is also the 8 micron image, which I showed in the previous slide. And on top, the sign contour is the same N2H plus contour, but now I add in the magnetic field orientations, which is shown in the yellow segments here. So here with this study, and also previously we showed the multi-scale magnetic field orientation, we want to really perform a multi-scale study of the magnetic field orientations. And by connecting the cloud scale here in JCMT to the smaller scale magnetic field orientations. And of course, the magnetic field is important. We expect the orientation should be quite similar from large to small scales. And also we want to characterize the large scale filaments magnetic field properties as well, including by studying the rectifier orientation between the filaments and the magnetic field orientations, and also to study their magnetic field strength. So to really visually guide how the magnetic field orientation go changing towards the hot molecular core positions, let's go a little bit visually inspection. So looking at here, this is where the G31 hot molecular core position is. So when we focus this is the orientation with an average orientation, which is going, I would say, northwest to southeast. And then this is about -45 degrees, which is we're going counterclockwise from the north. As we're zooming in, which is now going back to the SMA, which I showed earlier, this is the magnetic field segment as SMA. I also highlight these continuum sources, including the 4 protocluster sources seen in Bertrand et al. 2021 on the same figure. And also the black segment here is the cloud orientation from JCMT. So I'm overlaying this same panel. We see that the overall orientation remains very similar. And then, of course, when we go to closer, again, what we're doing a zoom in. This is the 1.3 millimeter ALMA study with the magnetic field orientation on top. Again, you can see this. See this self-similar hourglass, and orientation is similar. And now, even if we go to the 3 millimeter, visually it seems to be quite close to each other. So when we overlay all this vector into the same panel, this is what we see. So this is, again, the black segment is the cloud scale. The cyan vector is the SMA core scale. And we keep zooming down to 1.3 millimeter ALMA scale, and even to the yellow vector, which is down to the circumstellar scale by the 3.1 millimeter ALMA data. We see that the overall orientation is following the cloud scale. So we think that this is interesting, and also highlighting again these 4 protocluster sources. And also here there are 2 processes. One is corresponding to the center of intensity, one is corresponding to the center of mass. So we want to quantify how similar indeed this smaller scale magnetic field orientation to the cloud scale. So what we do is we center at each of the position, including the 5 continuum source. We see that in the earlier SMA images. And then we do from there and enlarging the aperture size. And we measure the mean and the standard deviation of each of these aperture size. And then what we can do is we are tracing how the magnetic field orientation changes with respect to the cloud scale field orientation at different space scales. So this is what the result is. So this here, the x-axis is the scale in AU, and y-axis, this symbol is the angle differences between the small scale magnetic field orientation and the cloud scale. So you can see the color, different color here is corresponding to different positions, including the 5 continuum positions, the 4 protocluster sources, and the center of mass position. So what we can really see tracing from the center of mass position, which is following by the red dots here, the angle differences remain very low. So what really indicating is where the mid average orientation of these structures is similar, which is very low, is 20 degrees, going down all the way to circumstellar scales. And also we can see as we looking at the scale, which is about 10,000 AU, about there we see the angle distance is almost the same as what we visually inspect. So that means it's independent of where the position is along the region, either it's from the core in the protoclusters. However, of course, when we are going down to 10,000 AU scales, we're seeing these angle differences compared to the cloud starting to deviate. But interestingly, you can see, especially focusing A, B, C, and D, which are the 4 protocluster sources, A and B, which is more intense and locating more closely at the center of the hourglass, magnetic field morphology, having continuously low angle differences from the cloud scale. But then the sources, which is C and D, which is further out from the center of mass positions, actually having a larger angle differences. But then also that these angle differences seems to be increased with decreasing peak flux, because we measured the peak flux from Maida 2021 paper, and she found that the A and B is more intense and the C and D is much more less intense, but they are more sitting outside. So how do we understand this, and what would be the implication on the high mass star formation towards the G31 molecular core? So one of the things we think that is the increase in, at least this increase in the 10,000, below the 10,000 AU seems to be consistent with other studies, which is by Zhang et al. 2019. They have assembled some of the other high mass star forming regions, but also low mass star forming regions. They see that seems to that the smaller scale magnetic fields start to forget the cloud scale orientation at around 0.01 parsec scale. So in here, the A and B are the most 2 intense sources. So what happened is we think that the source A and B, which is more intense, are dominating the gravitational well towards the core. So when the material keep inflowing to the center of A and B, what happened is we will start dragging the field lines as well, the core scale and the circumstellar scale with them. So what happened is this is what we see in these self-similar magnetic field orientations at the smaller scales. And even more interestingly, because of the C and D, which is outside, further outside from this collapsing point, so maybe they are really less influenced. But when we're looking closer to the 3 millimeter polarization data, we also seem to find that there seems to be a symmetric, also well-defined magnetic field orientation, and even maybe a hourglass morphology. So in fact, what we are seeing that the magnetic field continues to playing a quite important role even down to the circumstellar scales. So what we are saying from this study, from this multi-scale view of G31 magnetic field orientation, is that the magnetic field regulates massive star formation from the cloud to the circumstellar scales. So now we move to the next goal of this is to really study the magnetic field properties in the filaments. So here we actually identified and measured the filament orientation via the Hessian matrix analysis, and we actually identified 8 filaments. So here we have, which are indicating the contours of all these filaments, and also we read the resulting filament orientation map and then compute the pixel by pixel angle differences between the filament ridge orientation and the magnetic field orientation directions. So the magnetic field segment here is all in the pixel scale, which is of 1 JCMT beam. So here 1 pixel scale is 1 JCMT beam. So what we do is we do the angle differences between the ridge orientation and the magnetic field. What we are seeing here from the north, we're seeing is much more, I would say, less messy. You can see from the color scale, so the relative orientation between the filament and the magnetic field seems to be relatively parallel, but then now going to the southern part, which is a little bit more messy. But when we do the average, which is taking the average of the relative orientation, we found a predominantly parallel alignment between the filament and the magnetic field. So what we are thinking here, then we actually doing one of the film. So some of the filament was actually further excluded from the analysis. So in the end, we would say there's like 5 filaments that we are really studying. So what we are doing to further constrain is the filament magnetic field strength. So what we do, we are applying the DCF method, which is that Davis-Changa-Fermi method, as well as a modified version of the DCF method, which is provided by Skalatas and Tessis 2021. So here's just the 2 equations which to estimate the plane of sky B field strength. So we use the N2H plus to estimate the velocity dispersion, and then we use number density, which is actually inferred from N2H plus and 850. Actually, in the result, we found a quite similar magnetic field strength. So the estimated magnetic field strength ranges between 0.06 to 0.23 milligauss. So we use this number to compare other infrared dark cloud study. We found that it is actually quite consistent. So in this case, I would say that the magnetic field seems to be playing also an important role in the large scale of G31 as well. So now we are sampling this, but we are saying that the filaments, as we're saying, that how do we understand the larger scales and even what we can learn about the formation of the G31 hot molecular core. So what really we are learning from here is that what we can see, this parallel alignments maybe could be explaining the different scenarios that the gas could be acting as a channel to guide the gas towards the hot molecular core of the G31 hot molecular core. So this actually could be seen from another study, which is by Pillai et al. 2022 towards the 7 South region. And also what we can learn is that these filaments could be parallel to have cloud field alignments. How would they form and fragments? This may be related to one of the study which the turbulence gas can accumulate along this dynamic important field and form filaments that is parallel to the magnetic field orientations. So now, one of the things that we also see, as I mentioned, in the larger scale image here is this arc-shaped filament morphology. So as we mentioned, this seems to be sitting next to the bubble. And the magnetic field orientation is really following the magnetic field morphology. This tangential morphology is actually not surprised. Actually, this has been seen in other high mass star forming region, which is, for example, NGC 634, which we think that there's this magnetic field orientation or morphology is relating to the expanding bubble. So in this case, if this is the case, I mean, we can actually expect there to be some influence from the compression of this bubble in the west on the formation of the G31 hot molecular core. I mean, one of the things we want to further confirm is by this whether really checking if it is indeed the case we have this gas infilling inside towards the G31. We really want to use the gas kinematics, but of course, like we need really higher resolution study to really go following whether there's a velocity gradient, which is towards further north and south of the G31 cloud region. So from here, I actually want to take a short summary about this work. So this work is we carry out and study the JCMT pole to polarized dust emission at 850 micron with 2 goals. The first goal is we want to study overall magnetic field orientations, which is remain similar cloud to the circumstellar scales. And this, we think that this self-similar smaller scale magnetic field, including we can see this really nice hourglass going down to the circumstellar scale, suggests that the magnetic field which is dragged by this infalling material going into the most intense source, which is dominating the gravitational well. The second goal of this study is really to characterize the magnetic field on the larger scale. As I mentioned, we see that the ordered magnetic field morphology and the parallel alignment seems to suggest that magnetic field play an important role, because otherwise we expect the feedback or turbulence really severely affecting the magnetic field orientations. But then now, as we say that the DCF also estimate the magnetic field strength, which is quite strong, from 0.06 to 0.23 milligauss. And we propose, and I think one of the scenario, we think the most possible way is maybe this magnetic field is really guiding the gas in, and then towards the central part where G31 hot molecule is forming. So this is more or less the work I've been working on the G31. So another thing is towards the, I would say the later part of the talk, I want to talk about another things, which is the MAGMAR or MAGMAR survey. So this is the G31 that I've been showing quite in a few slides as well, but this is one of the source. We have one of the source we're doing this multi-scales. But then we really want to expand this to a larger sample and especially in different environments to really study, wait, what is really the role of magnetic field indeed playing an important role in different cases or not? And here there are two surveys. One is the MAGMAR survey, which is the magnetic field in massive star formation survey. Another is the magnetic field in massive star forming region, or MAGMAR survey, which is with the PR of Patricia Sennheiser. So here, especially in the MAGMAR, we actually get a bunch of samples, which we already have really observation from the very small scale, from the VLBI, from the SMA, from the core scale, and we also have many of them. We also have the cloud scale from JCMT, or actually there will be coming observation from the NICA 2 observation as well. So this actually allowing us to collect a good sample which have all spanning from cloud to circumstellar scale. And we again to do this similar study of what we did on G31 from doing the magnetic field orientation or even characterizing the magnetic field properties, then we can really have a good idea what is the role of magnetic field in magnetic field Hammer star formation as well. So one of the sources that I will be really have a study here is the G16.5 So just to make sure the people online can hear in case.
Yes, we can hear you. Yes, Paul.
Yeah. So what I just saying is that in this interesting source is sitting in a very big contrast of environment. And this is where the source is. So this on the right here is the 1 millimeter dust continuum map of this source. What we can see, we're already seeing this really, I would say, highly fragmented. And there are already at least like 7 bright continuum sources in the field of view. So this big green circle is the primary beam, and then the red circle, which is also showing in this panel, is where we will expect to have a good polarization detections with good signal to noise. So this is where the line is. We also, interestingly, we're also seeing some filamentary structure going out, and also especially this like arc structure, which to me, this is very interesting as well. So one of the key things at least I want to study the magnetic field orientation of these sources. So again, on the left, I'm just putting the continuum. Now I'm overlaying the magnetic field orientation with a signal to noise cut off. On this case is free from the price intensity. So from here, we can see a very interesting magnetic field morphology, especially toward the main source. We're seeing this really nice kind of hourglass, which is suggesting maybe, again, how the magnetic field might play a role. But interestingly, we can see this almost 90-degree flip horizontal magnetic field orientations, which to me is interesting, and I don't know what that really means, which I'm trying to understand. And then you're also seeing that there's some magnetic filaments really tracing some of these more diffuse filaments, so might be indicating some maybe gas really accreting towards the sources, or maybe something else. We don't know. This is one of the goal of this study towards these sources. And also we're seeing that there's this really southern sources, which is here, which might be that, given what this collapse is really bending the fields. This is actually one of the really strong hot molecular core in this region. So this is very interesting as well, because how this magnetic field orientation, not just looking into the dust continuum, but also we're looking into gas as well. So as a quick look, I mean, this is just a PV diagram, which is really indicating the inflow and outflow, which is happening in this region. There are multiple outflows, which is showing us indicate from the PV diagram. So the 0 here is indicate at the center of the source in the previous slide, which is at where the central source is, where the central hourglass and turning to this horizontal magnetic field orientation is. And we can see all this really nice outflow and inflow signature of it. And also this, if I'm doing a diagonal cut, and then across the 3 blobs on the continuum, and just do another cut which diagonal, this is another one of the PV diagram. So one of the key or study of this work I'm working on is hoping to link the magnetic field orientations with the outflow orientations and maybe the velocity gradient directions. And these are some of the works that I would want to study as well. So I think this is actually my last slide, and I would want to thanks again for giving me a chance to give a talk about the G31 and about the G16 sources, and I will be willing to start and take questions.
All right. It's time for questions. So please, Mara.
Okay, so great talk, Paul, about year 31. I have so many questions. I would like to know if you have an idea of the magnetic field strength in the small scales. You have mentioned in the scales a values of 0.2, if I remember well, milligauss. Assuming a temperature is 20, but it seems to me the temperature is low, considering that this is a high mass star formation region. I would like to know if you do an estimation about the magnetic fields, strength, and more scales, in particular in the position of the several protostars, A, B, C, and F.
So yes, indeed, well, this is something I should have also mentioned, but thanks for asking this. So actually, the magnetic field from the core to the really circumstellar scale have been studied by Joseph Miguel in 2009, when they estimate the magnetic field strength to a few milligauss, and even down to the circumstellar scale when Maita studied the to scale from 2 watts to different sources around 10 to 15 milligauss. So this is very strong magnetic field towards on that. But then I think one of the interesting thing is we see that the filament is about 0.06 to, I would say, 0.2 milligauss. How the magnetic field strength, or even I would say how the mass to flux ratio, for example, really going from the large scale to the smaller scale. There's another thing that we should and we could actually follow up on this.
But we can see that increase of the magnetic field as we go to the small scale. You said
yes, this is indeed what we see. Yeah, and indeed, we think that the 20 Kelvin is one of the empirical estimates which is taken from the normal infrared dark cloud studies. So we take the average. When we say average, it's also quite.
It was so interesting.
Yeah.
I don't know how sensitive is the magnetic field.
Yeah.
To this value.
Any other questions?
Yeah, very, very interesting things. I want to go back to the morphology of the filaments that you showed before.
You mean the angle differences or?
Well, when you show the map of the different regions, the limit, where you show the shapes of the different filaments that you identified.
Like at the very beginning in introduction, or?
No, I think it's a couple here, exactly, yeah. So I'm not exactly sure what the definition of filament is. I'm sure, well, you mentioned the method that you use to identify them. I'm sure it's not a straightforward method, but I want to know what defines a filament in your case.
So yeah, so I think I will go a little bit to the technical detail here. So here, first, when we say filament, it's relatively close and dense, which we actually define as the 8 micron absorption feature. And also one other thing, you think that the filament should be quite elongated. So in the basic way of saying that aspect ratio should be at least greater than 2 or even more, but then you have elongated things. So one of the technical things here, we're actually using, we first define a kind of a boundaries of this region based on the intensity map of 8 micron. So we are using a kind of a contrast. We take the intensity ratio of the pixel to the maximum and we plot the histogram. And then we take, because these are really dark, these are actually the outlier from the map, because if we do the distribution, most of the field regions should be in the center because of the dominant part, which is we actually see more Gaussian distributions. And those actually really the outlier is actually those which is really, I would say, the high contrast, for example, in the 8 micron, because this is really the absorption feature. And this actually allow us to kind of define more the region in the filaments. And also to further check on the things, we also check the coverage of the N2H plus. Do we have N2H plus detection? Because this is one of the N2H plus is really one of the good trace of this dense gas and filament as well. So this help us to really define the region, and then from there we also applying the Hessian matrix analysis to allow us to identify dissecting into filaments and also the orientations. So I don't know if this answer your question about how to the filament.
Yeah, more or less. I'm asking the question from the point of view of an untrained eyes, especially when it comes to magnetic field. So my question was more like what constitute, for example, a filament? Is it so when you take a single filament, for example, what is common among all the material within that filament? Is it the magnetic field direction, or is it something else? So you are showing in this map here you have different, directional magnetic field. So when you take a single filament, do you expect all the fields to be pointing in the same direction?
Well, this is a very good question, and in fact, one of my previous study before before I'm doing the high mass star formation, I'm studying the magnetic field orientation towards the Goldberg cloud. So what will happen with one of my previous supervisor, Hui Li, is found that magnetic field, the orientation can form actually along the field lines, if it's magnetically important, can be either by anisotropic collapsing by this compression, it leads to a filament which is elongated perpendicular to the magnetic field orientations. But on the other hand, if you have gas reaccumulating along the field line, as I mentioned, then you can have a filament which is finalized, will be having the filament parallel to the magnetic field orientations. So in fact, this is when you pick a filament, actually it is not just parallel, it could be perpendicular. And of course, I mean, this will be even more complicated. I mean, assuming, of course, magnetic field is important, of course, you get compression, it will be bended. But then if in the cases which is now the magnetic field important become less, then you may have more different morphology. Like, yeah.
Any other questions? We're here.
Thank you for my story. Is there any kinematical criterion to distinguish the filaments? Because one would expect some kind of coherence within a given filament that can differentiate it from another. It has been taken into account here.
So I would say here I use based on we looking in the NDH first integrated intensity, but for this analysis which I showed in the report, I identify and separate the filament based on the 8 micron web. So in this case, I have not really used the gas kinematic. If you're meaning to using gas kinematic to really dissect the filaments, no, this is what I didn't do that. But another thing which realized, if you, for example, we go to Bertrand et al. 2022, if we look into, for example, NDH process, we can also see quite different or more kind of filament morphology in this case. So I don't know on that. So this might be things that I can also use the gas kinematics to separate the filament, if this is what you mean.
But I mean, for example, there is a mean velocity in a filament which is different by a few kilometers per second from the other filament and so on. So within the filament, you can have velocity gradients, for example, that trace the kinematic of the filament itself. But sometimes you can see a characteristic velocity of one filament which is different from the other and different from the other. So in this way, you can differentiate the different filaments. In addition to the morphological differentiation because of the elongation or the orientation of the magnetic field, but the kinematics itself can be a way to distinguish between filaments.
So yeah,
you
but in this
line
case,
emission, you can do it probably.
Yeah, thanks. But just to clarify, I mean, in this case, I did not use the gas kinematics only based on the 8 micron.
Okay.
But indeed, using the gas kinematics indeed could provide another mean to separate filaments because they should be having a coherent velocity, right?
Thank you.
Yeah.
Well, thank you for the very interesting work. I was about to ask about more or less the same that Guillaume does, actually. Yeah, but apart of that, I was wondering whether for instance, turbulence, high turbulence, or other kind of kinematic effects that you can find in this kind of objects affect at the small scales, it would affect the distribution of the magnetic field. So you have a very turbulent region, or you have an outflow, a jet, these kind of things. So is that sort of that would that produce a sort of a negligible feature, or that would be interpreted as a more fundamental?
Well,
change?
I would first go back to this figure. I mean, one of the things, that is why we want to study the orientations. I think one of the first hints, or at least to me, one of the first signal, if that the turbulence really dominating or alpha dominating, it is that it will be the framework orientation really got quite random, and this is not ordered. And also you will be really going, the gas flow or the outflow direction of the field has to be like really following of that. First, I don't think this is what we see from what these studies. And also, given that the magnetic field orientation is similar from the cloud to the circumstellar scale, at least I don't think turbulence and feedback have a very severe effect. Of course, at the 3 millimeter, I mean, we have starting to see some, I mean, increasing angle differences, which might also contribute to the effect of increasing significance and contribution from turbulence and the local feedback. But as I mentioned, even source C and D, they are also quite aligned with a quite well-defined orientation, which is almost 90 degrees, not something like random 45 or 30 degree turbulence, like just chaotic. You would expect to drag the line to any directions, but it's not the case. And also, while I'm not showing here, we think that we also see quite a symmetric magnetic orientation center in C and D. So it means that this could be also a tentative hourglass. And this is another really good signature that actually is the really fail regulated contraction as well.
Okay. Thank you.
Yeah.
Okay, so we have time for final questions, if there is any. I think it's you want a final?
Perhaps this is a naive question. What happened with the ultra-compact regions in, I didn't know there is an ultra-compact region to the east in the G31. Have you mapped also the ionized gas with polarization observation and infer the magnetic field for the companion, I mean the ultra-compact region that perhaps triggered the formation of the hot molecular core in J31?
I have not able to really immediately capture the position, but maybe not. But as long as if we, because if
you go back to the previous slides when you has in the background the 8 microns, this one.
yeah, I mean, but you can see at least even though, I mean, this, because one vector, the separation, this, remember this one vector is one beam side. So the JCMT beam is 14 arcsecond. So if the ultra-compact, I remember the ultra-compact actual region is about 5 arcsecond away, I think it is not resolved. But assuming if it is like everything is beam, then we have a well-defined direction, which is the same. But of course, when we go into smaller scales, that's another question. And of course, I mean, this is something that we definitely will perform if we have such coverage.
Okay, so I suggest then to thank Paul again. Thank you very much, Paul. And now we're gonna teach in the fine art of tapas. So everybody is welcome, and we go somewhere nearby. Okay, so everybody welcome. Thank you.
Hey, great talk, man. That was really nice.